Hello everyone, good afternoon. Welcome to the class ECE341, the probability and stochastic process. Today we will keep working on the stochastic process. We gave the definition last time, right? Okay, this is a ECE341 for the 13th week. This is a Wednesday's class. Okay, stochastic process. You can think a stochastic process is also just a random process. It is a sequence of random variables. So we have x of t or x of n, and for each t or n, xt or xn is a random variable. Okay, that's it. The definition just looks like this. But you try to describe these random variables, that will be very complex. Actually, we just use the normal way to describe those random variables. We have CDF, we have PMF, or PDF, right? We have three functions. We can use these three functions to describe of each xt or xn. Right? We have all these functions for each one, and when you have some, for each, and for some of it, so sum it for some several. I should say several. Okay, for several random variables in the sequence. In the process, we have joint, CDF, PMF, or PDF. Right? We have all of these. This part is very complex. Right? You can imagine several random variables. You can pick 2. You can pick 3. Like for this discrete time random variable random process, you pick any two, like x1 and x10, x2 and x5, x100 and x200. Any 2 you can have joint CDF. Then any 3 you can also have joint CDF. And any 5 of the random variables, or every 20 of these random variables, then you can consider joint CDF. That will be a lot. Yeah. Okay, this is one thing. Functions. Then related with these functions, these distributions, we can have the for each x of t or x of n, we can calculate this kind of things. We can consider e of x of t or e of x of n. Same thing. It's a similar thing. Right? Variance of x of t or variance of x of n. Right? You also have the deviation of x t or xn, right? What else do we have? Yeah, you can have similar thing. You can have similar thing like the moment, the case order moment, or this one, right? The moment, yeah, something like that. And then for each pair, like xt1, xt2, or x of n1, x of n2, and this is this one. Then we can have covariance, right? We can have covariance and covariance coefficients and correlation coefficients. X, not xy, both are x, xt1, xt2. Yeah, I just put rho something and r something, right? We can have all of these. Okay, compare with these functions, these numbers actually somehow simpler than those functions, right? Simpler than this function. So, okay, so this is all of these are coming from previous knowledge, right? Just for random variables, we already have these. Then we can have something, we do some simplify. What kind of simplify? We consider some special process which can make the make this not so complex. When you study those kind of process, these kind of things can be simpler than general case. So we have 3 types of random process. The first one, we have IID process. IID process, independent, identically distributed process. So that means x, like x t, for any t, has the same distribution. Or xn, x of n for any n, has the same distribution. The second is if xt1, xt2, you have 2, they are independent. They are independent if t1 do not equal to t2. Or maybe you consider discrete time, then it's xn1 and xn2. If n1 do not equal to n2, similar thing. The IID. Actually, we know this, right? We call this as use a different name. We call this as a independent ensemble trail of random variable x, right? That is x1, x2, x3. You take samples, whatever samples do you want. You list all your result. Each one is a random value, so you have a sequence of random variables, and all of them, they are independent and they have same distribution with x. So this is a IID. Yeah, this is IID. So this IID just kind of generalize of this one, because in here you have x of n. When you consider discrete type random process, the stochastic process, this n could be run from negative to positive infinity. And when you consider, you take samples of this x, usually you have xn here. Like you take 1,000 samples, then from x1 to xn. And here the n will run from negative to positive infinity. This is a little bit different. And also we have continuous case. And for sample of a random variable, usually we only have like finite numbers, not all the time. That's infinite all the time. That's a lot, right? That's a lot. Here we only have several, you can say, several or tens or 100 or even 1,000, just finite numbers of the samples, right? So that's a little bit different, but the idea is the same. Yeah. Okay. Then the second one we call is stationary process. stationary process, then the distribution, they have this one. They have the distribution, I write this one. Distribution of xt1 until xtm is as same as the distribution of xt1 plus tau, xt2 plus tau, xtm plus tau for any t1, t2 until tm and any tau, like this. Stationary. So you consider several, you pick several random variables from the process, you consider the distribution of them, and you change the index, change the time, you add some number for all of them, then you have a new set of random variables, right? Then these random variables, they have the same distribution. So this one and this one, they have same distribution for any t1 to tm and any tau. Alright, so we call this stationary process. This kind of things, like I would say, like any IID process is stationary. You got it? Yeah. But of course, we have some different kind of process. They are stationary, but they are not ID. So the things like I use these to represent all the stationary process. Then the ID process is a part of it. ID process is a part of the stationary process. The ID might be too simple, we cannot use it for some complex cases too simply, and then we consider more wider processes. So this is stationary process, and this feature is very good. Then a lot of distributions, they are same. If we do not have this kind of condition, you generally consider the distribution of this process. You pick any finite numbers of the random variable from the process. You have the joint CDF, PMF, or PDF. Then that gives you a lot of functions. But a stationary process, in a stationary process, you have less function you need to consider, because a lot of them, they are same. Of course, here I said t, so maybe you can also write for discrete time, that will be x of n1 to x of nm, like this, right? And these are x of n with some k plus I still use a tau, okay, but this time this tau should be integer, okay, like this. K run from 1 to n, right? Yeah, for discrete time process, we use this notation. And the distribution means CDF or PDF or PMF, right? CDF for any kind of random variable. For PDF, that means X is a continuous time process, a continuous value process. And the PMF, the X is a discrete valued process. Okay. So this is stationary process. Okay. Then we have another one. It's a third type. Third part is wide sense stationary process. This kind of process, they consider even more processes. That is, the feature of this kind of process is the mean of any x of t is a constant. It's a constant. I denote it as a mu, just a mu, constant. And then the covariance of x t and x of t1 and t2, this one will equal to covariance of, as t2. I write this as t1 plus a tau. Okay, this one same way is covariance of x of 0 and x of tau, like this for any tau. So we have these two features. Okay, so for wide sense process, we didn't do any restriction. We didn't give any restriction on the distributions. We just say their mean and covariance satisfy these two conditions, and we can see that. So any stationary process is wide sense stationary. So this one even wider. So we have like an IID process is part of stationary process. And stationary process, all the stationary processes, they are part of the wide sense stationary processes. It's like this. Okay. Well, this one contains more processes, and this one will be easier to work on it, because here we do not need to take care about the distribution. We still need to use the distributions, but we have a lot of cases we just need to do the calculation on those average values, variance values. We only need to work on these. All right. Okay. So we have this three kind of processing. All right, this is what we studied last time, and actually all these points, they are the main topic about the stochastic process in our classes. All right, now let's study some examples and some more details about all of these kind of things. Consider an example. We consider a process like this. We consider IID process x of n. Now n run from negative to positive infinite with distribution okay, normal. All right, normal distribution, Gaussian distribution, mu sigma squared. And here I just put the mu and the sigma squared. If you want, you can change this to be some numbers, some values. Then you can try to like a kind of practice on all the rest part of this example. Here, then we can consider several things. The first one, we can consider the find distribution. Or discuss distribution. Here, because this is a continuous value, we just need to discuss the PDF. That will be fine. Right? PDF, this is continuous time process. And secondly, we want to find those average values. And third one, we want to check. We know this is ID. Okay, yeah, we already have this. We know it must be a stationary and wide sense stationary process, but we can verify. verify it is a stationary process and also a Y-sense process. Y-sense stationary process. Right. We can do this three kind of works. Okay, first one for the distribution, we want to find the PDF. Right. For the distribution, we need to study the PDF, right? So we have two kinds of PDF. The first one is for every xn. Fxn of x, what it is? We know it is Gaussian, right? It is Gaussian, this one. So it is a square root of 2 pi times sigma 1 over it. Here's e to the negative 2 sigma square in denominator, and numerator will be x minus mu square. That's it. Right. This is just a definition of Gaussian distribution. And then for any two random variables in the process, we say Lec13W and Lec13W. Then we consider Fxn1 and n2. We want the joint distribution x1 and x2. We want these. What is this? Okay, we know it is independent, right? ID process. It's ID process. So for different n, they are independent. They are independent. Of course, here n1 do not equal to n2. They are independent. So they were equal to Fxn1 times Fxn2, right? Independent, because they're independent. Right. Okay, so then you just multiply two of things like this. There will be 1 over 2 pi times sigma square and the exponential power. Now you need a times 2 of this kind of thing together, right? So there will be summation of the powers. So it is a negative x minus mu square over 2 sigma square minus another, it is x1. Another one is x2 minus mu square over 2 sigma square. So it is 2 pi sigma square 1 over it, and here is a e. Okay, I'm writing this way. Exponential power. Here's a negative 1 over 2 sigma square. Then inside is x1 minus mu square plus x2 minus mu square. Right. You have these. You have these. If you want to know more details, you can try for different values of mu and sigma. Like mu is 0, sigma is 1. Then what it is? Mu is 1, sigma is like 3. Then what it is? You can have a more study, more details about it. So here I just leave it like this. Then for any random variables in the process, any set of there's a set of random variables in the process. I say x of n1, x of n2, x of n, capital N. Alright. Then of course we suppose n1 do not equal to ni do not equal to nj for all of these n's. They're different. Alright. Then similar thing, because they're independent. Now they are independent of each other, so we have x of n1, x of n2, x of n, x1, x2 to xn. They are the multiplication of all of these together. So we use a notation, a capital Pi. This means multiplication of lot of terms, and each term they are similar thing. It's a square root of 2 pi and sigma in the denominator, and the numerator is exponential power of negative I minus mu square over 2 sigma square, and I will run from 1 to this n, and writing this way. And then if we do some simplify, we merge all of this together, it will be square root of 2 pi sigma to the power n's, and then exponential power. Inside the exponential power we have summation. It will be 1 over 2 sigma square times summation of all of these. I say summation of here I run from 1 to n. Each term is xi minus mu square. Now we have this. So this is the joint distribution. Joint PDF. So we have this. So actually this happens usually for ID. When you consider an ID process, you want to find the distribution for any set of any set of random variables in this process. Then the joint distribution, it is just the multiplication of each one. Alright, this is for ID process. Okay, this is for the distribution functions. Right, we have all the cases. Then I have 3, right? Second one, we consider average values. Average values we have several kinds, right? The first one is mean value, e of x, for any x. So for any x of n, we have e of x of n. We have notation. We denote this as mu x of n. Okay, I just write this. Mu x of n will equal to e of x of n. And okay, this is we know x of n is obey the normal distribution with mu sigma square. So this one, it is just mu. And then we can consider the variance of x, which is a variance of x of n, which is here just a sigma square. If here's a n mu, if here's a n of mu is 1, sigma square is 9, then here will be 1, here will be 9. Alright, now sigma square, right? Not the square. And if you want sigma x, that will be square root of variance. That will be just a sigma. Now for this case, it will be 3. Okay, this is for single one, for any one. Then for any pair, for any x n1 and x n2, for any pair of random variables, then we have this one. We have covariance of x of n1, x of n2. Oh, the notation. You know what? This one, if you read different literature, different books, this will be denoted as C x of n1 and n2. This is common use. Actually, this is common use. Common use notation. And here in our book we write in this way. This is n1, and this number will be the difference between these two, so that will be n2 minus n1. This is a notation in the textbook. Yeah, I don't know, the author of the textbook, he changed some notations. He didn't use the common use notations. He used this one. So you should know this. All right. Here I will still use this one because all the homeworks and the solution manuals we use this. I use this notation. We use this notation. Okay. But you should keep in mind when you read some other books or other like papers, research papers related with these kind of things. They denote it usually they denote in this way. Yeah, this is a natural way actually. Okay, anyway, we just use this one. Use this notation. So Cx of n1 and I say m. Okay. This is x of n1 plus m. M is the difference between n1 and n2. This is nm is covariance of x of n1 and x of n1 plus m. Okay, is this one. Then this one will be what? We know it is independent, so in this case it is 0 because of the independent. 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 Okay, because independent. So it is just 0. Remember, we have studied this, right? We have this formula. If they are independent, this is 0. And actually, we have another similar thing is Rx of n1 and m, which is defined as E of x of n1 and x of n1 plus m. Yeah, this is notation in our textbook. Then this one will be E of x of n1 times E of x n1 minus plus m is like this. So each we know they are mu, right? This is mu, this is mu, this is mu squared. So we have this. All right. Do we have any other kind of random the average values? No, we have other average values here. Okay. After we have these average values, we can look at them. We can study them. Can we find something here? You can see for mu x and sigma x squared for the mean and the variance and the standard deviation, they are constant no matter what are these n's, right? No matter what are these n's. And for the covariance, covariance, we have these. This is constant. Oh, we have one more. This is m do not equal to 0. This is also m do not equal to 0. If m is 0, they are same thing. Right? So we cannot use these rules. Okay, I didn't finish. Let me write two more formula here. So we consider when m is 0, so we have Cx of n1 and the m, or just n is fine. Okay, Cx of nm, they are equal to 0, or the covariance of just the x n and x n plus 0, which is n, if m is 0, if m do not equal to 0. So I write what it is. Actually, this is what? This is just the variance of x of n, right? just variance of x of n. So variance, we know this is a sigma square. It's a given value if m do not equal to 0, and 0 if m equal to 0. Alright, this is Cx. And Rx, n, and m, similar thing. If m is not equal to 0, it is mu square if m do not equal to 0. And if m is 0, then this is a e of xn with a square, right? Okay, so this will be mu squared. And this one is variance of x of n plus e of x outside is a square. Right, we have this because variance is this one minus this one, right? So we have this. And okay, so this is a sigma square plus mu square. Okay, this is if m do not equal to 0. This is if m equal to 0. So we have Rx, Cx like this. Alright. Okay, and then we can say these two functions only depending on m. Only depending on m, right? No matter what is n, the value will be same. But for different m, the value are different. So these two related with m. Oh, I have a name. I didn't mention the name. What is Cx? Cx is covariance, but here we have different name. We call this is a auto covariance. Autocovariance. And this one we call it auto correlation. Yeah, this is covariance, but we have special name just for the stochastic process. We call this autocovariance. And this is a correlation. We know these are correlation. We call it autocorrelation. Okay. Okay. Yeah, I have the third one. We have finished all the calculation, right? I have third question. Yeah, we finished 3 part of this example, and I have the third one. What is third one? I remember I have third one. Right? That's it. Okay, we want to see. We want to verify it is a stationary process as well as a Y-sense process, right? Y-sense stationary process. Okay, then we can check. 3. Check. Stationary. That means the distribution like f x n, it is equal to f x of n plus n in m, and f x of n1 to n it is equal to f x n1 plus m until x n plus m plus m, same m. Here's x1 to xn. Are they same? You change the index, you add some m in the index, then do you have the same distribution? You can think like this. This is time n. Then for every n, you have x of n here. This is n. X of n will be a random variable. It will take some values, right? Here means 0 or something, some values here. And for different n, this is n1, another n2, you have another random variable. Then you consider the distribution. Distribution of this one, you shift it by m, you add m here, you have x of and 2, which is x of n1 plus m. You change this to be this one. Do they have the same distribution? Do they have the same distribution? This is one thing, right? And if you have several x, then you remove all these forward by m. They have the same distribution. Then you have several x of n. You have several random variables from the process. Each one you have a distribution, and then you move the index forward by m. Then you have similar set of process. Then the joint distribution of the moved shifted random variables and the given random variables, do they have the same distribution? So these are these two questions, right? Then I will say yes, right? You check. We just by part 2. In the part 2 we have studied in part 1. Right? This is part 1. Part 1, for a single distribution, we have this one. Right? You add m in the index. Anything change? Yeah, you add m in the index. Anything change here? You see, this is n, right? But inside the function, no n. So no matter what is n, it is always like this. So you add some m here, doesn't matter. This distribution function is the same. The PDF now is the same. Okay, and for joint distribution, it's like a joint of 2 variables. Then here, if you n1 plus m and 2 plus m, do you have anything change here? No, right? The same, right? The same. Here, no m, no index occur here. Similar for the last one, for this one. If you add m here, is n1 plus m and 2 plus m, you add m here. Right? You want to check whether when you add m here, the index, all of this you add m, then the result will be what? Same, right? Nothing changed here. Yeah. So I will say yes. Yes. This is also yes. So we say stationary, no problem. Stationary. Yeah, it is stationary, no problem. Alright. This is for stationary. Then the second we check the Y-sense stationary. Y-sense stationary, we want 2 things. Mu x of n, is this a constant? Actually, yes, right? Yes, we calculated. Mu average values. Yeah. Average values. Wait. Too much paper. Okay. We have mu x of n. The mean value is a constant, right? It's a constant, no matter what is n. Okay, this is yes. Second one, we want to check Cx of n and m, whether this equal to Cx of n 0 m, sorry, 0 m. Yes. Oh, this one, I gave this formula in the covariance, in the form of covariance. That means covariance of x of n and x of n plus m equal to covariance of x of 0 and x of m. Whether these are same. So that means when you consider 2 variables from this is n, right? You pick n and you plus m. This is n plus m. Then you have 2 random variables. You check the covariance between them, and then you consider Okay, I put a 0 here. That means n is a negative value for convenience to show the graph here, right? This is n equal to 0 here, and this is just m. N and m. This is n plus m. This is 0 and m. Then you check the covariance between these two. Okay, these two values are same. That means, you move these anywhere. If you move them together, they move these two in the same distance in the time to anywhere, to here or to here. If you keep their distance do not change, you do not change their distance, then the covariance will be same, right? This is the meaning of this. And here we do the calculation. We know the covariance is result is down here. Covariance is where the I see it. We have this one. Cx and m equal to sigma square or 0 depending on the value of m. So you see, this one and this one, they are same no matter what is n. N is 0 or doesn't matter, right? Here's n, but the result only depending on m, no matter what is n. So you replace n by 0 here, the value won't be changed. They are same. Okay, I will say yes. Alright. So this is it is a y-sense stationary process. Alright. Okay. So this is one example. Alright. It's almost the class are done. Okay. Then that will be all for today. I put the problem here. Next time I will still study this one, but we consider a different thing. Now let y of n equal to like x of y of n equal to x of n plus x of n plus or minus 1. Okay, and I time some constant like 2 and 3. Then study the process y of n, and let zn equal to 2 of x of 2n plus 3 of x 2n minus 1, and study the process zn. Okay, last time we studied these two. Xn is the same distribution as the same distribution in the ID. This is ID Gaussian. Then we want to study these two different process. Alright, this is that next time we will do this. Okay, and I also have some homework problems. Then actually you can start to do that homework problems, because all the knowledge, all the formulas, all the materials just based on the previous knowledge. So for random process, for the stochastic process, all the formulas, all the calculations, just some old calculations. The difference is here we have a lot of random variables, not just 1 or 2 random variables. Alright, okay, then that's all for today. See you next time. Bye bye.